While much is still uncertain about the origin of ion channels, we have reason for arguing that they arose from a common ancestor. Ion channels present in an abundance of varieties today, and so we divide them into families. When looking at evolution, members of the voltage-gated superfamily are suspected to precede other families of channels because they are found throughout all domains of life. This suggests that their existence is extremely ancient, and many speculate it may be as ancient as life itself. To further support this idea, we can break down a voltage-gated channel into its constituent parts, a pore module and a voltage-gated module. On the left of this picture, we see the voltage-gated module in purple and the pore module in teal. On the right, we see the voltage-gated module functioning independently in a voltage-gated phosphatase. Likewise, the pore module is found to function independently in streptomyces. It is hypothesized that the first subunit of a channel came about by their fusion. So here on the top left, you can see we have a voltage-gated module that has 1, 2, 3, 4 membrane-spanning regions. And on the top right, we have the pore module that shows 1, 2 membrane-spanning regions. And in between those, we have the pore loop. As these would have combined, they would show the figure below, which is a single subunit of a voltage-gated potassium channel. And that shows us that there are 6 membrane-spanning regions as well as the pore loop that have been conserved. Shown in the top row is this first subunit we just formed, known as the alpha subunit. The combination of 4 of these subunits would form one voltage-gated potassium channel. Below, in that second row, we see the structure of calcium and sodium channels. They are formed by one polypeptide with 4 internal repeats. Each of these repeats is called a domain, and the domains are numbered 1 through 4. With each domain resembling that of the alpha subunit, each with 6 membrane-spanning regions and a pore loop. This increase in complexity indicated the likelihood the potassium channels came first, while the calcium and sodium channels arose from a series of 2 duplication events, once to 2 domains and again to 4. So with all of this in mind, we have strong reason to believe the first voltage-gated ion channel was a potassium channel. We can visualize the joining of 4 alpha subunits here. We see one individual unit, and as they conjoin as a tetramer, they produce a channel. So, what does a voltage-gated potassium channel really look like? If we return to visualize the alpha subunit of a potassium channel once again, we can begin to construct a functioning channel. A single subunit has 6 membrane-spanning regions, which are labeled S1 to S6, and the P region that denotes the pore loop that will later form the pore of the channel. Regions S1 to S4 are the voltage sensing domain, while S5 to S6 are the pore domain. A crystallized subunit is shown here, allowing us to see more shape of the unit. In here, we see how the units combine to form a channel. In this image, only 2 subunits are used for clarity of the pore. The region at the top of the image is formed by the P loops of each subunit and is deemed the selectivity filter. It is labeled here as the upper gate. And lastly, this shows the crystallized structure when all 4 subunits are conjoined. Another way to visualize the filter is in a 2-dimensional version I've drawn here. The 4 segments represent the 4 subunits and are viewed looking down from the outside of the cell. The triangular pieces in the center, making up the main circle, are the pore domain, S5, S6, and the pore loop, with the pore loop oriented to the opening of the channel. The external circles are the voltage domain, S1 through S4. We can see here how the domains align to form the channel. Angling of the subunit beneath our view causes them to appear disjointed, but they are still continuous as shown before in the individual subunits. Each color here represents one of the 4 subunits, though to clarify, they are still identical in structure to one another, even though they differ in color. So now that we have an idea of what a potassium channel looks like, we're going to focus on how it works. More specifically, we're going to determine how the channel selects for potassium ions over other ions, such as sodium. We know that potassium and sodium ions are both positively charged, and that potassium ions are larger in diameter than sodium ions. A potassium ion has a radius of 1.33 angstroms, while a sodium ion has a radius of 0.95. When a potassium ion approaches the channel, it is in its hydrated state. We see the potassium ion in green entering the channel from the interior of the cell. In order for the ion to enter the constrained region of the channel, The hydration shell must be removed. In its hydrated state, the ion is simply too wide to pass. The center of a pore is lined with carbonyl groups, which we see enlarged on the right side of the page. These are spaced in a fashion that arrange the oxygens of the carbonyl groups in an almost exact spatial arrangement of a natural hydration shell. Thus, when the water molecules are removed, the potassium ion fits snugly into the channel and is bound in an energetically favorable manner. When a hydrated sodium ion approaches, it too must have its hydration shell removed to enter the channel. However, there are two reasons that this ion will still not pass. First, sodium has a higher hydration energy than potassium. To review, larger ions have lower hydration energies because the water molecules are further away from the nucleus, and thus their attraction is weaker. Sodium's higher hydration energy makes its dehydration energetically unfavorable in comparison to potassium. Secondly, is the difference in bond distance of the hydration shell and the carbonyl groups. Here we see a hydrated potassium ion. The blue dotted lines show us the length of the bond between the ion and the water molecule, which we call bond distance, and this value will be noted as X. Here, the blue circles represent oxygen atoms of carbonyl groups, and we can see how a potassium ion would fit between them. The space between a potassium ion and these carbonyl groups is a new bond distance and also happens to equal X. Thus, the bond is energetically favorable and happens easily. For a sodium ion, we can denote its bond distance with the hydration shell as Y. Here, we show the same four carbonyl group oxygens and how a sodium ion would fit between them. Because the sodium ion is smaller, the bond distance here is much greater than that of the potassium ion, and similarly much greater than Y. Thus, the binding of a smaller sodium ion is not favorable. In conclusion, both the higher hydration energy and the geometry of the carbonyl groups in the channel make passage of a sodium ion highly unfavorable when compared to potassium ions. The function of the selectivity filter is highly conserved between potassium channels, and it is also highly efficient, allowing 10 to 100 million potassium ions through in a single second with small error. Without the accuracy and efficiency of these channels, life would not have been able to evolve like it has today. However, there is still much to be learned about ion channels and their unique qualities. If you're interested in learning more, please follow any of these sources. And for more fun neurobiology topics, please follow #BrainyTigers on Twitter.